Right now, as you watch this, the Earth is under siege. Not from anything human-made, not from a missile or a virus or a storm you can see rolling in on a weather radar. This is something older and more powerful than anything civilization has ever had to contend with. A wall of charged particles launched from the surface of the Sun at millions of miles per hour has just slammed into our planet's magnetic field with a force that scientists are calling the most severe geomagnetic event in 23 years. The skies over Texas are glowing green. Astronauts on the International Space Station have been ordered into shelter. Power grid operators across North America and Europe are watching their equipment with white-knuckled focus, and the agency responsible for protecting us from space weather just upgraded their alert to the second highest level on the scale. This is not a drill. This is not a theoretical future scenario. This is happening right now. And to truly understand what that means, you need to understand what the Sun actually is, what it just did, and why the people whose job it is to watch the sky are not sleeping tonight. Let's start at the source. The Sun is not a ball of fire. That's the first thing most people get wrong when they try to picture it. Fire is a chemical reaction, the rapid oxidation of material in the presence of oxygen. The Sun has no oxygen. What the Sun is a sphere of plasma, a fourth state of matter so energized that electrons are ripped entirely free from their atoms, leaving behind a roiling, churning sea of charged particles held together by gravity and driven by nuclear fusion at its core. At the center of the Sun, the temperature reaches roughly 27 million degrees Fahrenheit. Under those conditions, hydrogen atoms are forced together so violently that they fuse into helium, releasing enormous quantities of energy in the process. That energy takes tens of thousands of years just to work its way from the core to the surface. Then it crosses the 93 million miles between us and the Sun in about 8 minutes. Every second of every day, the Sun converts around 600 million tons of hydrogen into helium. The energy released by that process is what warms our planet, drives our weather, powers photosynthesis, and makes life on Earth possible. Without it, Earth would be a frozen rock drifting in the dark. But the Sun is not a steady, reliable engine. It breathes. On an approximately 11-year cycle, the Sun moves between periods of relative calm and periods of intense activity. During the quiet phase, called solar minimum, the surface is relatively smooth, sunspot activity is low, and solar flares are rare. During the active phase, called solar maximum, the surface becomes turbulent and chaotic. Dark regions called sunspots appear across the face of the Sun, and these are not just cosmetic blemishes. They are regions where the Sun's magnetic field lines have become tangled, concentrated, and extraordinarily powerful. We are currently approaching solar maximum, and the Sun knows it. The sunspot that triggered this event was one of the most magnetically complex formations scientists have observed in years. It had been rotating into view for several days, and space weather forecasters were already nervous. The magnetic field lines threading through it were wound up like a coiled spring, storing energy in the way that a fault line stores stress before an earthquake. The only question was when that energy would release. It released all at once. A solar flare is one of the most violent events in our solar system. In a matter of minutes, a region of the Sun can release more energy than 1 billion hydrogen bombs. That energy explodes outward from the surface in the form of X-rays and ultraviolet radiation, traveling at the speed of light. Those rays reach Earth in 8 minutes. We cannot warn anyone. By the time instruments detect the flare, the radiation is already here. But the flare is only the opening act. Behind the radiation comes something slower and more dangerous. When a solar flare is powerful enough, it tears a hole in the Sun's corona, the outermost layer of the solar atmosphere, and sends billions of tons of magnetized plasma erupting into space. This is called a coronal mass ejection, and it is the thing that is currently pressing against the Earth's magnetic field like a battering ram. Unlike the radiation, which arrives in 8 minutes, a coronal mass ejection takes 1 to 3 days to cross the distance between the Sun and Earth. That travel time is both a blessing and a curse. It gives forecasters a window to prepare. But it also means that for those 30 to 72 hours, scientists can do nothing but watch it come. When the ejection from this particular event was detected, the measurements were alarming. The cloud of plasma was dense, fast, and carrying a magnetic field oriented in exactly the worst possible direction. Here is why that matters. Earth has its own magnetic field, generated deep in its iron core. This field extends far out into space, creating an invisible bubble called the magnetosphere. Under normal circumstances, the magnetosphere deflects the constant stream of particles flowing out from the Sun, what scientists call the solar wind. The magnetosphere bends that flow around the Earth the way the bow of a ship parts water. Life on Earth has existed under this protection for billions of years, and without it, the atmosphere would slowly be stripped away by the solar wind, the way Mars lost its atmosphere billions of years ago. But the magnetosphere has a weakness. It is not perfectly sealed. The Sun's magnetic field can interact with Earth's magnetic field in a process called magnetic reconnection. When the two fields are oriented in opposite directions, they can link up and essentially punch holes in our protective bubble, allowing solar particles to pour directly into the upper atmosphere. The magnetic field embedded in this coronal mass ejection was oriented almost perfectly southward, which is exactly opposite to the northward pointing field on Earth's day side. The collision was not a glancing blow, it was a direct punch. The NOAA Space Weather Prediction Center, which is the agency responsible for monitoring and forecasting space weather in the United States, issued a severe geomagnetic storm watch, rating the event as what they call a G4. The scale runs from G1 to G5. G1 causes minor grid fluctuations and is barely noticeable. G5, the most extreme category, is the kind of event that can collapse power grids across entire continents. This event at G4 sits just one step below the worst possible scenario. This is the strongest storm to hit Earth since the Halloween storms more than 2 decades ago. Before that, you have to go back to events in the 1980s and 1990s to find anything comparable. For most people on the ground, the most visible and beautiful consequence of this storm is the aurora. Under normal circumstances, auroras are confined to the polar regions. The charged particles streaming in from the Sun follow Earth's magnetic field lines down toward the poles, where they collide with nitrogen and oxygen molecules in the upper atmosphere. Those collisions produce light, the shimmering curtains of green, red and purple that people travel to Iceland and Alaska to see. But during a severe geomagnetic storm, the zone where auroras are visible expands dramatically southward in the northern hemisphere and northward in the southern hemisphere. Reports flooded in from across the United States. People in Texas, people in Florida, people standing in their backyards in states that have never once seen the northern lights looked up and saw the sky on fire with colour. Cities as far south as the Mexican border were photographing auroras overhead. Social media filled with photographs and videos. Some of them looked almost too beautiful to be real, and some people thought they were. But they were real. Every single one of them was being produced by the same storm, by the same particles from the same explosion on the Sun that had been travelling toward Earth for the better part of 2 days. It was one of the most spectacular mass astronomical events that ordinary people have witnessed in a generation. But the people responsible for keeping the lights on and the satellites running were not watching with wonder. The electrical grid is one of the most vulnerable systems on Earth when it comes to space weather. Here is why. When a stream of charged particles interacts with Earth's magnetic field and causes it to fluctuate, those fluctuations induce electrical currents in long conductive structures on the ground. Power lines, pipelines, railway tracks. These structures act like antennas, picking up energy from the changing magnetic field and channeling it in unexpected ways. The currents induced by a severe geomagnetic storm are called geomagnetically induced currents, and they are not like normal electrical current. They are quasi-direct current, meaning they flow in one direction with very little fluctuation. The transformers that sit at the heart of electrical grids are designed to handle alternating current, the kind that switches direction 60 times per second in North American systems. When you force a large direct current through a transformer designed for alternating current, it saturates the iron core of the transformer. It overheats. It can fail permanently. The large high-voltage transformers at the core of the grid are not off-the-shelf items. They are custom-built. Each one can weigh hundreds of tons. They take years to manufacture and cost millions of dollars. If a major storm knocked out transformers across a wide region simultaneously, replacing them would take not weeks but potentially years. In the worst-case scenarios modelled by researchers, a sufficiently extreme storm could leave large portions of a continent without reliable power for an extended period of time. Grid operators know this. They have been developing protocols to manage the risk. During severe geomagnetic storm warnings, operators can pre-position equipment, reduce loads, temporarily take vulnerable transformers offline, and prepare for rapid switching if problems develop. These measures reduce the risk significantly, but they do not eliminate it. During this storm, operators from Canada to the United States to Europe were actively managing their grids in real time, watching geomagnetic field sensors for sudden spikes and making adjustments. In some regions, voltage fluctuations were detected. In others, protective equipment triggered automatic responses. The grid, for the most part, held. But the margin was not comfortable, and the grid is not the only concern. Satellites are exquisitely sensitive to space weather. Every satellite in orbit is exposed to the full force of whatever the sun throws at us. There is no atmosphere up there to absorb the energy, no thick blanket of air between the solar particles and the spacecraft's electronics. The radiation from a major solar event can permanently damage solar panels, scramble computer memory, and in extreme cases completely disable a satellite. During this storm, satellite operators went into what is called safe mode. They oriented their spacecraft to minimize the exposed surface area facing the incoming particle stream, shut down non-essential systems, and prepared to wait out the bombardment. But there is another effect on satellites that most people never think about, and it is one of the stranger consequences of geomagnetic storms. The upper atmosphere, when energized by incoming solar particles, expands. It heats up and puffs outward, reaching higher altitudes than it normally would. For satellites in low orbit, this means they are suddenly flying through air that is slightly thicker than it was before. That extra drag slows them down, and when satellites slow down, they lose altitude. They begin to fall. During extreme events in the past, satellites have had their orbits decay so dramatically that ground controllers struggled to maintain accurate tracking and had to perform emergency reboost maneuvers. During this storm, the concern was particularly acute for the constellation of small commercial satellites in low orbit that the world has come to rely on for communications, navigation, and data services. Many of those satellites are small and have limited propulsion. If their orbits decay faster than expected, there is very little they can do about it. GPS is another system that takes a direct hit during geomagnetic storms. GPS works by measuring the precise travel time of radio signals from satellites to receivers on the ground. But those radio signals pass through the ionosphere, the charged upper layer of our atmosphere, on their way to you. Under normal conditions, the ionosphere introduces a predictable delay that GPS receivers can account for. But during a severe geomagnetic storm, the ionosphere becomes turbulent and irregular. The delay changes rapidly and unpredictably. GPS signals flicker and jump. Accuracy degrades. In some cases, the signals drop out entirely. For most people, a degraded GPS means their navigation app gives them slightly wrong directions. That is annoying. But GPS is woven into systems far more critical than driving directions. Precision agriculture, air traffic control, financial transaction, time stamping, emergency dispatch, and military operations all depend on accurate GPS timing and positioning. When geomagnetic storms hit hard enough, all of those systems feel it. During this event, aviation authorities issued notices warning pilots about potential GPS degradation over certain regions. Flight operations in high-latitude routes, the paths that go over or near the poles, were particularly affected because those routes pass through the regions where geomagnetic disturbance is most intense. Some flights were rerouted to lower latitudes, adding time and fuel cost to transoceanic crossings. There is also the matter of the people who are closest to the storm of all. The astronauts aboard the International Space Station are already living in an environment that would kill an unprotected human being in seconds. The station orbits at an altitude of about 250 miles above the Earth's surface, far above the protective blanket of atmosphere. Radiation from ordinary solar activity is a constant concern for the crew. Over the course of a 6-month mission, an astronaut accumulates radiation exposure that would take years to accumulate on the ground. Mission planners carefully track lifetime exposure limits for each crew member. During ordinary days, the station's structure provides some shielding. The aluminum hull and internal equipment absorb some radiation, and the crew can reduce their exposure by spending time in more heavily shielded areas of the station. But when a severe solar particle event occurs, those ordinary precautions are not enough. The station does have a dedicated shelter, a specific section designed with enhanced radiation protection. It is not spacious, it is not comfortable, but it is the safest place on the station when the sun is angry. When mission controllers on the ground saw the data coming in from the solar particle monitors, they made the call. The crew was instructed to move into the radiation shelter and remain there until the worst of the event passed. Think about that for a moment. Imagine being one of the most highly trained individuals on the planet, someone who has spent years preparing to live and work in space, and being told to stop whatever you were doing and go hide from the sun. It is a reminder that no matter how sophisticated our technology becomes, we have not yet figured out how to make human beings safe from the full violence of what our own star is capable of. The astronauts did exactly what they were told. They moved into the shelter, stayed in contact with the ground, and waited. Space is patient. The storm eventually passes, but the waiting is not nothing. This is not the first time Earth has experienced a severe solar storm, and the history of these events is worth understanding, because it tells us something important about what we are actually dealing with. In the summer of 1859, a telegraph operator in Philadelphia sat down at his machine and noticed something strange. The equipment seemed to be working on its own. Messages were being sent and received even though the batteries had been disconnected. The telegraph lines themselves, energized by currents induced from the sky, were functioning as their own power source. This was one small, almost comical footnote to the greatest solar storm in recorded history. The event, now known as the Carrington event after the British astronomer who observed the solar flare that caused it, was so powerful that auroras were visible around the world, including in the tropics. Telegraph systems, the high-tech communications infrastructure of the day, failed across Europe and North America. Some operators received electrical shocks from their equipment. Papers caught fire. The Carrington event is the benchmark against which all solar storms are measured. Scientists estimate that it was significantly more powerful than anything that has occurred in the modern era of satellite technology and interconnected power grids. What it would do to our modern infrastructure if it happened today is a question that keeps space weather scientists awake at night. A detailed analysis by researchers at a major insurance and risk analysis firm estimated that a Carrington-scale event hitting a modern technological society could cause trillions of dollars in damage and potentially leave millions of people without power for months to years. The societal consequences, for systems that depend on electricity for water treatment, food storage, medical care and communications, would be profound. More recently, in 1989, a powerful geomagnetic storm caused the complete collapse of the electrical grid serving the Canadian province of Quebec. 6 million people lost power in about 90 seconds. The outage lasted approximately 9 hours, which was long enough to cause significant economic disruption, but short enough that the human cost was manageable. Had the storm been more powerful, or had it affected a larger region, the story might have been very different. In 2003, the Halloween storms, which currently hold the record as the most powerful geomagnetic event in the modern satellite era before this one, damaged approximately a dozen satellites, disrupted radio communications around the world, caused power outages in Sweden, and forced the FAA to reroute high-altitude flights. Each of these events left scientists more convinced that the risk from extreme space weather is not just real, but systematically underappreciated. And yet, compared to the risks from more familiar natural disasters, space weather receives relatively little public attention. You can insure your house against flooding and fire. There is no market for solar storm insurance. Most people, if you asked them, could not tell you what a G4 storm is, why it matters, or what they should do if one hits. Part of that is because the worst effects, the ones on power grids and satellites, are largely invisible to ordinary people until they experience the consequences. The aurora is beautiful. The failed transformer is not. The degraded GPS signal is just an inconvenience until it is not. The line between a storm that causes minor disruptions and one that cascades into a serious emergency is not always clear until you have already crossed it. What makes this current event particularly significant beyond its raw intensity is the timing. We are heading towards solar maximum, the peak of the sun's 11-year activity cycle. That peak is expected to arrive within the next year or two. What we are seeing now is not the worst the sun will throw at us in this cycle. It is a preview. Solar maximum does not guarantee extreme events. Some cycles peak without producing any truly exceptional storms. Others are littered with them. The physics that governs exactly when and how powerfully the sun will erupt is still not perfectly understood. Forecasters can identify dangerous sunspot regions and track eruptions after they occur, but predicting with precision when a particular sunspot group will flare, or how powerful that flare will be, remains beyond current scientific capability. What scientists can say with confidence is that as we move deeper into solar maximum, the probability of additional major events goes up. The sun will be more active, sunspots will be more frequent and more complex. The conditions for large flares and coronal mass ejections will be more commonly met. This means the warning that space weather researchers have been trying to communicate for decades is now more urgent than it has been in a long time. The infrastructure of modern civilization, our power grids, our satellites, our communications networks, our financial systems, our navigation tools, all of it was built with little to no protection against extreme solar weather. Progress has been made. Grid operators have better monitoring tools. Satellite designers have improved radiation hardening. NOAA and international partners have expanded their networks of solar observation spacecraft. Early warning systems are better than they were 20 years ago. But better is not the same as ready. The satellites that give us the best advance warning of incoming coronal mass ejections sit at a gravitationally stable point between Earth and the Sun, about 1 million miles away. They can detect the leading edge of an incoming storm and give scientists anywhere from 15 minutes to an hour of warning before impact. 15 minutes to an hour. That is the window in which utilities can activate emergency protocols, aviation can reroute, and satellite operators can put their spacecraft into safe mode. For some protective measures, that window is enough. For others, it is barely sufficient. And if the storm is fast-moving, which some of the most powerful ones are, the warning time can shrink to almost nothing. NASA has ongoing missions dedicated to monitoring the sun continuously. The Solar Dynamics Observatory provides a constant stream of imagery, watching every flicker and fluctuation on the solar surface. Other spacecraft watch the corona, track solar energetic particles, and measure the properties of the solar wind. These tools have given scientists a far more detailed picture of the sun's behavior than was available even a decade ago. But the fundamental challenge remains. Predicting space weather is hard. The sun is a complex system. Its magnetic field is generated by processes that operate deep inside, where no observation can reach. The surface activity we can see is only the visible symptom of internal dynamics we can only partially model. The researchers who dedicate their careers to this problem are not alarmists. They are careful scientists who work with incomplete data, limited models, and the constant awareness that the next major storm could come tomorrow or not for another decade. What they are, uniformly, is serious. They take the risk seriously because the physics demands it. If you want to understand why, start with the numbers. The sun is 4.5 billion years old. It has been producing coronal mass ejections for essentially its entire life. In any given 11-year cycle, several major events occur. Over the course of human civilization, which spans only the last few thousand years, many Carrington-scale events have surely occurred. We survived them because our civilization, until very recently, had no electrical infrastructure to damage. The infrastructure we have built since the Industrial Revolution, and especially since the digital revolution of the last few decades, changes the calculation entirely. We have handed the sun an enormous number of new targets, and we have built our way of life around assumptions of continuous electrical power and reliable communications that a sufficiently strong solar storm could invalidate without warning. This is the uncomfortable truth that this storm is forcing into view. The aurora over Texas is beautiful. The pictures people are posting from their backyards are genuinely stunning, one of the most spectacular natural phenomena on Earth, made visible to millions of people who have never seen it before. There is something profound about standing under that light and knowing it was created by the same star that warms your skin, that fueled the plants you eat, that has been the heartbeat of life on this planet for billions of years. But the same force that painted the sky green over the American South also pushed the astronauts on the space station into their shelter. It forced grid operators to intervene manually in real time to keep the lights on. It degraded the GPS signals that pilots rely on. It threatened satellites that carry everything from streaming video to weather data to military communications. The storm is a reminder that we live inside a solar system, not above it. We tend to think of Earth as a place apart, sealed off from the cosmos by atmosphere and distance and the comfortable bubble of civilization we have built. But that bubble has a boundary. The boundary is the magnetosphere, and the magnetosphere is not invincible. The sun can push through it when it tries hard enough. Right now, the sun is trying hard enough. What happens over the next 24 to 48 hours will determine how this particular event is remembered. If the grid holds, if the satellites recover cleanly, if the only lasting consequence is a generation of new aurora photographs shared on the internet, then this storm will be remembered as a spectacular but manageable event. A close call, perhaps, but not a catastrophe. If something goes wrong, if a major transformer fails in a critical location, if a cascade of problems develops on the grid or in orbit, then the story will be different. It will be the kind of event that forces governments and utilities and the public to finally take space weather seriously as a threat to infrastructure, not just as a source of beautiful night skies. Space weather researchers will tell you they hope it is the former. They will also tell you they would not mind if it scared people just enough to pay more attention, because the next one is coming. The sun does not stop. It breathes in and it breathes out on its 11-year cycle, and we are moving into a phase of deeper breathing. The peak is still ahead. The conditions that produce this storm will recur. The only thing we do not know is when and how strong. The people watching the sky tonight, the scientists monitoring their instruments, the grid operators checking their readings, the flight controllers tracking their stations, the engineers whose satellites are drifting through a sea of charged particles, they all know this. They know that what we are experiencing is not a once-in-a-lifetime freakish accident. It is a recurring feature of the environment we live in. It is what it means to orbit a star. For most of human history, we had no way to know when the aurora appeared above the poles, no instruments sensitive enough to detect the magnetic fluctuations in the ground beneath our feet, no telescopes powerful enough to see the surface of the sun. We were blind to all of it. The storm would come and go, and we would never know. We can see it now. We can measure it, track it, predict it with some degree of accuracy, and in some small ways prepare for it. That is genuinely remarkable. That is the product of decades of scientific investment and ingenuity, and the slow accumulation of understanding about a system that is still revealing its complexity. But seeing the storm coming does not mean being ready for it. That is the next step. That is the work that still needs to be done in the engineering of hardened infrastructure, in the development of better forecasting models, in the international coordination between space agencies and grid operators and satellite companies and governments. That work is underway. It is not finished. And right now, tonight, as the most powerful solar storm in 23 years continues to press against the boundary of our world, the sun is providing all the motivation anyone should need to finish it. Look up if the skies are clear where you are. If you're far enough north, or if the storm holds its intensity, you might see something your grandparents never saw from where you live. A green shimmer, a rippling curtain of light, the visible signature of a star doing what stars do. It is beautiful. It is dangerous. It is the universe reminding us, gently for now, who is really in charge. Part 1 of 3. The storm is still moving. Even now, as the initial impact begins to subside, the cloud of plasma continues to interact with the magnetosphere in ways that scientists are still trying to fully characterize. The northern lights will likely persist for another night or two, painting skies across a broader geographic range than any storm in recent memory. But the real question, the one that the specialists are focused on now, is not how beautiful the aurora will be. It is whether the cascading effects are over or whether we are still in the middle of them. Because here is something that almost nobody outside of the research community understands about geomagnetic storms. The damage they cause does not always happen all at once. Sometimes it comes in waves. The initial impact of the plasma cloud is one shock. But as the magnetosphere rebounds and readjusts, as the magnetic field lines reconnect and reorient, additional disturbances can propagate outward. There can be secondary pulses, minutes or hours after the primary impact, that cause their own problems. Grid operators know this. They are not just watching the current readings on their lines. They are watching the forecasts, watching the magnetometer data, trying to predict where the next surge might hit. It is an extraordinarily difficult job, made harder by the fact that the models that predict storm behavior, while much improved, are still not perfect. There is still a significant element of uncertainty baked into every prediction. One of the reasons the models are not perfect is that we have only been systematically observing space weather with sophisticated instruments for the last few decades. In the grand scheme of the sun's activity, that is nothing. That is a blink of an eye. The sun has been burning for 4.5 billion years. It has been producing coronal mass ejections that entire time, but we have been measuring them carefully with satellites for maybe 50 or 60 years. That gives us a limited sample. We have records of some major historical storms. The solar observations made by scientists in the 1800s and early 1900s provide some clues about very powerful events. We can measure the auroral displays described in old journals and use those as a proxy for storm intensity. We can study tree rings and ice cores, which contain records of radioactive isotopes produced by energetic particles in the upper atmosphere, giving us a way to estimate the frequency of extremely powerful solar energetic particle events stretching back thousands of years. What those records show is sobering. The Carrington event of 1859, which I mentioned earlier, was not a once-in-a-thousand-years phenomenon. The geological evidence suggests that events of similar or greater intensity occur on the order of once per 2 to 3 centuries, and the records, limited as they are, suggest that some events in the past were even more powerful than Carrington. In the late 1600s, there appears to have been an enormous solar event that happened to occur during a period in which very few people were systematically recording astronomical observations. We know about it primarily from the radioactive isotopes embedded in tree rings from that era, a layer of carbon-14 that stands out clearly in the dendrochronological record. Scientists call it the Miyake event, named after the researcher who first identified it. The available evidence suggests this event may have been significantly more powerful than Carrington. If it happened today, the consequences would be difficult to fully predict, but certainly catastrophic to the electrical infrastructure of modern civilization. The probability calculation is therefore straightforward and not particularly comforting. Somewhere between now and the next 200 years, Earth will almost certainly experience another event at least as powerful as Carrington. That is not a maybe. That is not a low probability tail risk to be managed by specialists. That is a when, not an if. And the infrastructure that will be exposed to it is considerably more fragile and more interconnected than anything that existed in 1859. The grid, of course, is not the only concern. There is another system that is deeply woven into the infrastructure of modern life, and it is one that almost nobody thinks about as a space weather risk. The financial system. Modern financial transactions operate on a global network that depends absolutely on precise timing. When you buy a stock, when a bank executes a transfer, when a cryptocurrency exchange processes a trade, the timing of these transactions is recorded down to the microsecond. The synchronization of timestamps across this entire system is maintained by atomic clocks, primarily at the GPS satellites in orbit. When geomagnetic storms disrupt GPS signals, they do not just affect navigation, they affect financial infrastructure. During the Halloween storms in 2003, some financial institutions experienced problems with transaction timestamping. The errors were small enough that they did not cause major disruptions, but they were noticeable. They were caught and corrected, but they provided a preview of what a more severe storm, causing a more complete GPS outage in certain regions, could do to markets. Imagine for a moment a scenario in which GPS signals are degraded severely enough over a wide enough area that financial transactions cannot be timestamped accurately for several hours. Imagine the consequences for markets that operate on the assumption of continuous, synchronized, reliable time. The resulting confusion, the trading halts, the disputes over transaction ordering and settlement, the potential for significant financial losses would cascade through a system that is already extremely sensitive to any disruption to its timing infrastructure. This is not a wild speculation. This is a risk that financial regulators and space weather specialists have actually discussed. It is not the highest probability outcome, but it is also not negligible. It is the kind of secondary consequence of a severe solar storm that most people would never connect to the sun in the first place. They would see it as a financial system problem. They would not necessarily understand that it originated in a cascade of charged particles that originated 93 million miles away. There is another layer to this as well. The internet infrastructure that supports everything from communications to commerce to government services relies on a global network of undersea cables that transmit data by light pulses traveling through fiber optic tubes. These cables run through the deep ocean, and they are well shielded from direct solar radiation. But they are connected at various points around the world to ground stations and other infrastructure that is not shielded as well. The connections between the cables and the power systems that run the ground stations and the switching equipment are potentially vulnerable. During a severe geomagnetic storm, if geomagnetically induced currents surge into the ground stations that feed power to the deep sea cable systems, equipment could be damaged. Internet connectivity could be disrupted. The scale of such a disruption would depend on how many ground stations were affected simultaneously and how quickly repairs could be made. In the worst-case scenario, this could contribute to a significant degradation of internet services across regions that depend on transoceanic cables for international data transmission. Again, this would not be a worldwide blackout. The internet is designed with some redundancy, cables can be rerouted, but a severe storm could cause significant disruptions to internet service in certain regions for hours or even days. And since internet infrastructure has become so integrated with communications, banking, emergency services, and just about everything else in modern society, even a temporary disruption would have ripple effects that extend far beyond the technical domain. This is the challenge of modern infrastructure in an age of solar activity. Everything is connected to everything else. The power system connects to communications. Communications connects to finance. Finance connects to transportation and supply chains. A failure in one domain causes immediate consequences in others. The system is no longer resilient to isolated failures. A solar storm is not an isolated failure. It is a widespread, system-level disruption that hits multiple infrastructure domains simultaneously. The engineers who design and operate these systems are aware of this. They think about it. But the challenge they face is that hardening infrastructure is expensive, and the probability of a given location being severely affected by a major solar storm in any particular year is still relatively low. The cost-benefit calculation does not always favour extreme protective measures. It is a calculation made by accountants and engineers and government officials who have to balance the cost of protection against the probability of needing it, which means that preparedness for extreme space weather across the full range of infrastructure systems is still less robust than space weather scientists would prefer. It is better than it was 10 years ago. It will be better 10 years from now. But right now, in this moment, as we are transitioning into solar maximum, the gap between the risk and the readiness remains uncomfortably large. One of the reasons the gap persists is that the people who work in power generation, satellite operations, aviation, communications and finance are not typically the same people who study the sun. The expertise lives in different silos. NOAA has a space weather prediction center, NASA has solar observation missions, universities have solar physics researchers. But none of them control the infrastructure that would actually be affected. That control sits with private and public utilities, private satellite companies, airlines, telecommunications firms. These are entities driven by financial considerations, operating within regulatory frameworks that are still catching up to the reality of space weather risk. There have been attempts to bridge this gap. The Disaster Mitigation Act of 2018 included funding for space weather research and preparedness. The White House issued an executive order in 2016 on coordinating space weather response. Various international forums have brought together space weather scientists and infrastructure operators to discuss best practices. But executive orders and forum discussions do not automatically translate into hardened transformers installed at substations or radiation-hardened microprocessors integrated into satellite designs. What does translate into those things is catastrophe, or the fear of it. The worry that a major event will happen and will cause sufficient damage that everyone will agree that prevention was far cheaper than recovery. This is not a desirable way to drive policy change. But it is historically how it usually happens. Society does not typically make large investments in disaster prevention until it has recently experienced or narrowly avoided a disaster. The storm happening right now, if it ends up causing significant economic losses, could be the wake-up call that changes the landscape. If it passes with minimal damage, the sense of urgency will probably fade again, and the slow process of incremental infrastructure hardening will continue. Right now, with the storms still ongoing, grid operators in several countries are still on high alert. They have managed it. So far, so good, but they are not out of the woods yet. The storm could develop secondary impacts. A transformer could fail from an unanticipated surge. A satellite could become unrecoverable. A section of critical infrastructure that was thought to be protected could turn out to be more vulnerable than expected. The next 24 hours are still crucial. Beyond the immediate crisis, though, there is a longer-term question that space weather researchers have been trying to push into the public consciousness for years. The question is not just what to do about the next Carrington-scale event whenever it comes. The question is what happens to a highly dependent technological civilization when you remove the assumption of reliable electrical power for an extended period. Let me be specific about what extended actually means. If a severe geomagnetic storm knocked out high-voltage transformers across a wide region, and if multiple transformers failed simultaneously making staged rebooting impossible, the utilities in that region would face a problem that does not have an easy solution. You cannot just replace a failed transformer quickly. These are massive pieces of equipment, built to specification, manufactured one at a time. If a transformer fails today, a replacement might take months to even construct. During that time, the region remains without power. Now, imagine this happening in a region with a population of several million people during the winter months in a cold climate. Or imagine it happening during the summer in a region that depends on air conditioning for survival. The cascading consequences become very clear, very quickly. The water system dependent on electrical pumps stops working within hours. Hospitals switch to backup generators, but those are not unlimited. Fuel to run the generators becomes scarce. The supply chain for food, dependent on refrigeration and transportation networks that require electricity, starts to break down. Communications fail as battery backups in cell towers run down. Heating fails in winter. Cooling fails in summer. The sewage system backs up. Sanitation becomes a crisis within days. In the developed countries with sophisticated emergency management systems, the response protocols exist on paper. Local governments are supposed to activate emergency operations centres, mobilise emergency services, manage rationing, organise shelter. But these systems have never actually been tested at the scale of a total power outage across an entire region lasting weeks or months. The assumption is that they would work, but there is no guarantee, and that is just the immediate consequences. Over weeks and months, the secondary effects start to pile up. Hospitals run out of fuel for generators, pharmaceutical supply chains fail, water treatment stops, disease outbreaks begin. Banking systems dependent on electronic infrastructure cease to function normally. Insurance systems, which are already stretched, become overwhelmed. Governments struggling to maintain basic services find that the normal mechanisms of governance are inadequate to the scale of the crisis. The research on this scenario has been done. It has been published. It is not relegated to obscure journals or fringe speculation. Serious researchers at reputable institutions have modelled what happens, and the conclusions are sobering. The consensus is that yes, a sufficiently severe solar storm striking a heavily populated region with vulnerable infrastructure could produce a genuine humanitarian crisis that would take months or years to fully recover from. Not everyone agrees with these models. Some argue that the estimates are too pessimistic, that infrastructure is more resilient than researchers assume, that the disruption would be manageable. Others argue the models are actually too optimistic, that the cascade of failures would be worse than modelled. But virtually no one seriously argues that the risk is negligible, or that we should be completely unconcerned. Yet the public awareness of this risk remains remarkably low. If you asked a random person on the street what a geomagnetic storm is and why they should care, most would have no answer. If you told them that a solar event could potentially disrupt electrical power to their region for weeks, many would not believe it. If you presented them with the scientific research, some would dismiss it as doomsaying. Others would assume that governments must already be taking it seriously enough to prevent such an outcome, which is a charitable assumption that may not be entirely grounded in reality. This is partly because space weather, as a risk, does not have the visceral, immediate quality of other threats. You can see a hurricane forming on a satellite image and watch it approach for days. You can understand the threat immediately. An incoming solar storm, by contrast, is almost entirely invisible to anyone without specialized instruments. There is no gradual build-up that you observe yourself. There is no weather report warning you to get to safety. One day the sky is normal, the next day there is an aurora that is beautiful, and then the next day the aurora is gone. The danger, from the perspective of someone on the ground, is entirely abstract. This is actually one of the reasons space weather researchers have been cautiously supportive of the aurora photographs spreading across social media during this current storm. Yes, the aurora is beautiful, and yes, most people taking those photos have no idea of the technical complexities or risks involved. But the fact that auroras are being observed and photographed across such a wide area, from locations where they are extremely rare, is visually proving something that researchers have been trying to communicate. It is proof that something genuinely extreme is happening. It is proof that the sun can produce effects that reach down to the ground and do something noticeably different than usual. If auroras at unusual latitudes can create a moment of wondering and curiosity, if they can push even a few people to actually look up and think about their connection to the cosmos, then the researchers are fine with that. It is a tiny first step toward a public that is somewhat more aware of space weather as a phenomenon and a risk. The long-term goal is more ambitious, though. The goal is a public that understands space weather enough to support the policy and infrastructure changes that would reduce the risk. That understands that investing in transformer hardening and satellite redundancy and improved forecasting is not wasteful spending, but insurance against a known risk. That understands that when government agencies allocate resources to space weather preparedness, that is not a trivial expenditure of money that could be better spent elsewhere. It is money spent on avoiding a potential catastrophe that would dwarf the expenditure many times over. This is not an easy case to make. The benefits of preparation are abstract. The costs are concrete. The catastrophe, if it happens, will be terrible. But the probability in any given year is still relatively low. From a certain perspective, it makes sense to let it remain someone else's problem, someone else's responsibility. From a broader perspective, that attitude is exactly what leaves civilization vulnerable to a known threat. The storm that is happening right now, though, provides a moment of opportunity, a moment in which space weather is actually in the news, in which people are looking up and seeing something that connects them to the sun and space in a direct way. A moment in which the risk is not hypothetical. It is happening. It is measurable. It is real. This is when you can actually move the needle on public awareness and public pressure for action. In the hours and days after this storm passes, assuming it does not cause truly catastrophic damage, there will be a brief window in which the story will get media attention. Scientists will go on interviews, documentaries will be produced, politicians will make statements about the need for preparedness. Social media will fill with "Did you know about space weather" posts. The window will not stay open long. Human attention drifts. The next big story will emerge, and if the storm ends up causing minimal damage to infrastructure, the sense of urgency will fade relatively quickly. But in those weeks and months, real conversations happen. At the federal level, at the utility level, at the international level, budgets are reviewed, plans are made, equipment upgrades are prioritized, engineers start designing redundancies and hardening systems that they had been wanting to upgrade for years but could not justify. The storm provides the justification. And then the window closes. The storm becomes a historical footnote. Life goes on. But the infrastructure is a little bit more robust. The systems are a little bit more resilient. The risk is a little bit lower. That is how you reduce your civilization's vulnerability to space weather. Not through a single grand gesture or a global agreement, though those would be nice, but through the slow accumulation of incremental improvements, driven by a combination of scientific evidence and occasional reminders from the universe that we should probably take this seriously. Speaking of reminders, we should talk about what is actually happening at the sun right now to produce these storms in the first place. Because while we have covered the basic mechanisms, there is a lot of complexity operating beneath the surface that explains why solar maximum is different from solar minimum, and why the activity levels change in the way they do. The sun's magnetic field is one of the strangest things in the solar system. In many ways, it does not behave like the magnetic fields you might be familiar with from childhood experiments with magnets and iron filings. The sun's field is not static. It is not a simple bar magnet configuration with a north pole and a south pole. It is dynamic, constantly changing, being generated by movements of plasma in the convection zone just beneath the sun's surface. Here is how it works. The sun is not solid. It is entirely made of plasma, and plasma can move. The outer layers of the sun, the convection zone, are in constant turbulent motion. Hot plasma rises from deeper layers, cools as it approaches the surface, and sinks back down. This rising and sinking of plasma, in the presence of the sun's rotation, generates the magnetic field through a process called the dynamo effect. It is the same basic principle that generates Earth's magnetic field, though the details of how it operates in each place are quite different. As the sun rotates, it does not rotate like a solid body. The equator rotates faster than the poles. At the equator, one rotation takes about 25 days. At the poles, it takes about 35 days. This differential rotation tangles up the magnetic field lines. They get wrapped around the Sun, concentrated into bundles, twisted into knots. These knotted regions of magnetic field are what we see as sunspots. A sunspot, when viewed through a telescope, appears as a dark region on the Sun's surface. The reason it looks dark is not because it is cooler material, though it is that. It looks dark because the intense magnetic field in that region suppresses the normal convective transport of heat, allowing the plasma there to cool relative to the surrounding material. But a sunspot is not a simple, static feature. It is the surface signature of a deeply rooted, complex magnetic structure that extends deep into the Sun. The magnetic field lines threading through a sunspot region are under enormous tension, like a rubber band that has been twisted and stretched. That tension stores energy. Lots of energy. Eventually, if the twist becomes great enough and the magnetic configuration becomes unstable enough, that energy releases. And when it releases violently. A solar flare happens when the magnetic field lines in a sunspot region suddenly rearrange, reconnect and relax back to a lower energy configuration. This is not a gradual process. It is a sudden event happening over minutes or seconds. The energy that is released by this rearrangement heats the plasma in the region to incredible temperatures, upward of tens of millions of degrees. That heat causes the plasma to expand explosively. Radiation is emitted across the entire electromagnetic spectrum, from radio waves to gamma rays. But wait, there is more, because the really dangerous part happens when a flare is energetic enough to erupt the chromosphere and corona above the sunspot. When that happens, the relaxing magnetic field lines, instead of just converting their energy into heat and radiation, actually accelerate plasma outward. They throw billions of tons of magnetized plasma into space at velocities ranging from a few hundred miles per second to several thousand miles per second. That is a coronal mass ejection. The fact that both flares and coronal mass ejections can be triggered by the same event in the solar magnetic field is why they often occur together. The flare, producing sudden radiation that arrives in 8 minutes, is often accompanied or closely followed by a coronal mass ejection, the slower moving cloud that takes a day or more to reach Earth. This is why space weather forecasters, when they see a major flare, immediately start looking for signs of a coronal mass ejection. The two usually travel as a pair. Now, here is the key point that connects this to solar maximum and solar minimum. During solar minimum, the Sun's magnetic field is relatively well ordered. Sunspots are rare. Magnetic tangle-ups are uncommon. Flares and coronal mass ejections happen, but they are infrequent. The storage of magnetic energy reaches lower peak levels. The Sun, in a sense, is well organized. It is not explosive. During solar maximum, the opposite is true. The differential rotation has been going on for about 5.5 years at that point, the time it takes to complete roughly half of the 11-year cycle. The magnetic field has become increasingly tangled. Sunspots are everywhere. Complex magnetic structures with the potential to store enormous amounts of energy form frequently. The Sun has become chaotic, turbulent, and prone to eruption. This is the phase we're entering now. The tipping point from minimum to maximum does not happen abruptly. It is a gradual transition. Activity starts ramping up. The number of sunspots increases. The frequency of flares goes up. Coronal mass ejections become more common. What was a rare event at minimum becomes a multiple times a week event at maximum. As we move deeper into this current cycle, deeper into solar maximum, the frequency of major events will continue to increase. Not every flare will be a major one, but major flares will be happening more often. Not every coronal mass ejection will carry a magnetized cloud oriented to deliver a devastating hit to the magnetosphere, but statistically there will be more attempts. And all it takes is one direct hit, one cloud oriented exactly wrong, one massive ejection propelled at high velocity, and Earth is getting hit with a solar storm comparable to or exceeding this one. That is the concern driving the urgency in the space weather community right now. This event that just happened, this major storm, this is not a one-time freak. This is the new normal for the next couple of years. This is what solar maximum looks like. Multiple major events, any one of which could be directed at us, any one of which could cause damage ranging from manageable to catastrophic, depending on its exact characteristics and where it hits. Right now, the fortunate thing is that the direction of the coronal mass ejection, the speed at which it travels, the orientation of its magnetic field, these are not things we have any control over. They are determined by the physics of the magnetic reconnection event that launched it and the configuration of the solar magnetic field at that moment. We cannot predict them precisely in advance. We can only wait and see what direction the next eruption happens to come from. But what we can control is how prepared we are for when it does happen. And that preparation, right now, in this window as we enter solar maximum and before a potentially even more destructive event hits, is the work that matters. The good news is that progress is actually being made. It is just slower than scientists would prefer. But progress is progress. One area where genuine advances have been made is in satellite instrumentation and modelling. The satellites that monitor the Sun are far more sophisticated than they were even a decade ago. The cameras and spectrometers that observe the solar atmosphere can detect a flare and characterize its properties in real time. The instruments that measure the solar wind can provide early warning of an incoming coronal mass ejection. The models that predict where a given cloud of plasma will go, whether it will hit Earth, and when impact is expected have improved significantly. The Solar Dynamics Observatory, which I mentioned briefly earlier, launched in 2010 and is still in operation. It provides a continuous stream of images of the Sun from multiple wavelengths, showing the details of magnetic activity on the solar surface. It can track an eruption as it develops and watch a coronal mass ejection accelerating outward. It has become an essential tool for forecasters. Beyond that, there are satellites that specifically monitor coronal mass ejections and their properties as they travel through space. The SOHO satellite, a joint mission between NASA and the European Space Agency, has been watching the Sun and tracking solar eruptions for over 25 years. Stereo A and Stereo B, another NASA mission, provide three-dimensional views of coronal mass ejections by seeing them from two different vantage points simultaneously. At the advanced position, the gravitationally stable point about 1 million miles from Earth toward the Sun, there is a satellite called DS-ECOVR that has dedicated instruments for measuring the solar wind and the properties of incoming coronal mass ejections. When a cloud is approaching Earth, DS-ECOVR is the early warning system, detecting it first and relaying information back to forecasters who then send out alerts. This network of observations is substantially better than what existed just 10 or 15 years ago. But there are gaps. There are no instruments in orbit to the sides or behind the Sun, so if a coronal mass ejection is launched in a direction that means it will miss Earth, there is no way to know for sure until it fails to appear at DS-ECOVR. And there are always gaps in the data, instrument outages, satellites aging past their designed lifetime and not being replaced, budget constraints that prevent new missions from launching. The ideal network, from a forecaster's perspective, would have multiple satellites positioned around the Sun, providing continuous coverage of solar eruptions from all angles. If we knew, immediately upon eruption, the exact speed and direction of every coronal mass ejection, the ability to forecast their arrival and impact would improve dramatically. But that kind of network does not exist yet. It would require international cooperation, significant funding, and a commitment to maintaining it over decades. It is not impossible, but it is not in place right now. In the meantime, with the satellites and instruments we do have, forecasters make do. They are remarkably skilled at working with limited data, making educated guesses based on patterns and physics and historical analysis. When they issue a forecast for when a coronal mass ejection will hit Earth, the typical uncertainty window is still about a few hours. Not ideal, but much better than no warning at all. Beyond the satellites themselves, a lot of progress has been made in understanding the physics of how coronal mass ejections interact with the solar wind and the planetary magnetosphere. The models have become more sophisticated. The simulations that run on computers that try to predict how a given cloud of plasma will behave as it approaches Earth and encounters the magnetosphere have been refined and validated against real observed events. They are not perfect, but they work reasonably well. One of the practical improvements this has enabled is better prioritization of alert levels. NOAA can now issue storm watches with better confidence that they will actually verify. The alerts can be more specific about which regions are at risk and what types of effects are likely. This allows utilities to focus their protective measures on the most vulnerable equipment and the most critical infrastructure. Another area where genuine progress has been made is in the hardening of infrastructure itself. Some utilities, particularly those that experienced problems in past storms or that serve areas with critical infrastructure, have begun replacing vulnerable transformers with more resilient designs. Some new equipment being installed is being built with space weather considerations in mind. It is not uniform across the industry. Some utilities are further along than others, but the trajectory is in the right direction. Satellite operators have become much more sophisticated in their responses to geomagnetic storm warnings. They have protocols in place. They conduct regular drills. They maintain communication networks to receive forecasts and issue commands to satellites. The response time has decreased. The success rate for protecting satellites from permanent damage during storms has increased. Is it enough? No. Space weather researchers would be the first to tell you that there is far more that could be done. The investment is still insufficient. The coordination between forecasters and infrastructure operators could be better. The international dimension could be stronger, but compared to 20 years ago, it is dramatically better. What concerns researchers more than the current state of preparedness is the trajectory. On the positive side, there is more awareness of the risk than there was a decade ago. There are more satellites watching the sun. There are more models and simulations running. There are more resources being allocated to the problem at various levels of government and in the private sector. But on the negative side, the infrastructure that is at risk is becoming more complex and more interdependent. The power grid is becoming more computerized, which makes it more vulnerable to rapid cascade failures if certain key points are disrupted. The reliance on satellite-based services is increasing. GPS is being woven into more and more critical systems. Communications networks have more and more traffic going through fewer and fewer cable landing stations. All of this means that the infrastructure is becoming more fragile even as efforts to harden it are increasing. It is a race between hardening and fragility, and it is an open question whether the hardening can keep pace with the growing complexity and interconnectedness of the systems. This is the kind of thing that keeps space weather scientists awake at night. Part 2 of 3. So what does actual solar maximum look like, and what should we be expecting over the next 2 to 3 years as we approach and pass through the peak of this cycle? The first thing to understand is that solar maximum is not a single point in time, it is a period. It lasts roughly 1 to 2 years, and it is characterized by sustained high levels of solar activity. During this period, the monthly average of sunspot counts reaches its peak. The frequency of major flares and coronal mass ejections reaches its maximum. It is the time when major events are most likely to occur. But it is not the case that every day during solar maximum produces a major flare or coronal mass ejection. The sun is still variable. There are weeks where activity is relatively calm, even during the maximum phase. Then suddenly, without much warning, a complex sunspot group crosses the solar meridian and a major eruption occurs. The pattern is somewhat random, which means that being in the maximum phase does not mean constant crisis, but it does mean higher risk, constantly present. The current solar cycle, which began in 2019 with solar minimum, is in the process of ramping up. We are not yet at maximum. The forecasts from NOAA suggest that we will reach the peak sometime in late 2024 or sometime in 2025. Depending on how you measure peak, we might already be approaching it, or we might still have several more months. But the key point is that we are entering the period when major events are most likely to happen. Some solar cycles are particularly active. The cycle that peaked in the year 2000, for instance, produced many major events and was generally considered a very active maximum. Other cycles are more quiescent. The maximum that occurred around 2013-14 was relatively quiet by historical standards. The current cycle, based on the activity level so far, is shaping up to be moderately active. Probably more active than 2013-14, but not as extreme as the 2000 maximum. But probabilities do not guarantee outcomes. Even a moderately active maximum can produce surprise events. A single extraordinarily powerful flare can happen, even if the overall cycle is not the most active on record. And conversely, even if the overall cycle is very active, it is possible for a particularly powerful event to be directed away from Earth so that we do not experience it. What we do know is that during the next 1 to 2 years, the chances of Earth being hit by a major geomagnetic storm are significantly higher than they are during solar minimum. The storm that is happening right now, at the leading edge of maximum, is the first major proof of that. But statistically, there will be more. How many more and how much more powerful they might be cannot be predicted in advance. But more is what we should expect. This creates an interesting situation for the grid operators, the satellite companies, the forecasters, and the emergency planners who have to think about how to manage the increased risk. It is not like a hurricane season, where the season has a defined start and end date, and meteorologists have reasonable predictive skill for roughly how many major hurricanes will occur in a given year. Space weather forecasting is much less precise. We know that activity will be higher during maximum, but we do not know precisely how high, and we do not know exactly when major events will occur. This means that the mental model for emergency preparedness has to be different. It cannot be based on predicting specific events at specific times. Instead, it has to be based on maintaining an elevated level of readiness throughout the period when the risk is high. It is like running a hospital emergency room at elevated staffing levels for 2 years because you know there will be more emergencies, but you do not know which days will have them. The financial cost of maintaining that elevated readiness is real. Grid operators have to keep extra equipment on standby. They have to maintain trained personnel ready to respond to emergencies. Satellite companies have to maintain communication networks to receive warnings and issue commands to their spacecraft. They have to keep teams on call for emergency response. Airlines have to maintain protocols for rerouting flights and have personnel trained to implement them at short notice. Government agencies have to maintain their forecasting capabilities and emergency response systems at high alert. All of this costs money. It is money spent on prevention, on things that hopefully will not be needed. But it is money that has to be spent to reduce the risk. And it is money that has to be spent even if the feared event never materializes. What makes this more challenging is that the people making the budgeting decisions, the people who have to authorize the spending, often are not the same people who experience the consequences if the protection fails. The utility executive is not the person sitting in a dark hospital losing refrigeration for medications. The airline CEO is not the passenger stuck at an airport for days. The government official is not the person dealing with contaminated water because the treatment plant is offline. This is a fundamental misalignment between the people taking the risk and the people paying for the protection. In theory, the regulatory framework and the emergency management systems are supposed to address this by imposing requirements on utilities and airlines and other entities to maintain certain levels of preparedness. But the regulations lag behind the science. They are not always as stringent as space weather researchers would like, and the enforcement is not always as rigorous as it should be. This is where public pressure-informed public awareness actually matters. When the public becomes concerned about a particular risk, when there is media coverage and social media discussion and political attention, the calculus changes. Politicians start asking questions. Regulators become more attentive. Budgets for preparedness programs become easier to fund. Public pressure essentially provides the missing alignment between the people making decisions and the people who would bear the cost of their decisions. This is one of the reasons that some space weather researchers have actually been quietly glad to see this current storm happen. Not because they want a catastrophe, but because a visible, dramatic event that captures public attention is more likely to drive policy change and infrastructure investment than 100 academic papers describing the risk. The counter-argument is that a truly catastrophic event might be needed before the necessary resources are allocated. The thinking goes that minor events, even dramatic ones like this storm, might be impressive but not destructive enough to really change behavior. Only when a major storm actually causes significant economic loss, when the damage bill reaches hundreds of billions of dollars, will the level of investment needed to prevent it become politically possible. This is the tragedy of disaster prevention. The optimal time to invest in prevention is before the disaster happens. But the incentive structure means that the investment usually happens after the disaster occurs. We build better earthquake-resistant buildings after a major earthquake. We improve aviation safety after major crashes. We upgrade water systems after contamination events. We harden infrastructure against solar storms after a solar storm causes massive damage. It is not rational, but it is predictable, and it is what we can expect to happen in the space weather domain as well, unless there is a significant shift in how risk is perceived and valued. Right now, that shift is actually beginning. This storm is providing a teachable moment. When people see the aurora and learn that it is caused by a solar storm, when the news reports that astronauts had to take shelter, when they learn that grid operators were worried about keeping the lights on, the connection is made real. It is not theoretical anymore. It is not a scientist talking about probabilities. It is something that is happening. The media coverage of this event over the next few days and weeks will be crucial. If the coverage focuses on the beautiful aurora and the rare phenomenon, the moment will pass without much impact. If the coverage also explains the risks, describes what could go wrong if a more powerful storm hit, and emphasizes that this is not a one-time event but a preview of what to expect during this phase of solar activity, then the impact could be greater. Some of the coverage will definitely focus on the beauty. That is unavoidable and actually not bad. The beauty draws attention, but the more thoughtful outlets will also dig into the science, the risk, the preparedness question. The documentaries will explore it, the educational programs will expand, and in that expanding conversation, understanding will grow. For space weather researchers and forecasters, the next few weeks and months will be a kind of intense advocacy work. They will be interviewed, they will write op-eds, they will speak at conferences and before Congress. They will try to communicate the urgency of continuing to invest in space weather science and preparedness. The window for that advocacy is open now. It will not stay open forever, so they are making the most of it. Let me take a step back and talk about something that often gets overlooked in discussions of space weather risk, and that is the psychological and behavioral component of living under the shadow of a threat that you cannot see. In principle, knowing that there is a significant probability of a major solar storm over the next couple of years should not change anyone's day-to-day life. The probability in any given day is still relatively low. The probability that it will hit with a direct southward orientation that maximizes impact is lower still. The probability that it will cause your specific location to lose power is lower yet. By the time you divide the probability down to the scale of an individual person in an individual location, the probability in any single day is quite small. But knowing that something with potentially severe consequences could happen is still psychologically different from knowing that it will not happen. There is a kind of low-level ambient anxiety that exists in the minds of people whose job is to prepare for a risk that may or may not materialize. For the grid operator watching the magnetometer, there is the awareness that any sudden spike in the readings could trigger the next wave of the storm. For the satellite operator, there is the knowledge that the spacecraft they are responsible for are vulnerable to radiation damage. For the emergency planner, there is the scenario planning, the constant thinking through of what they would do if the power grid in their jurisdiction were to collapse. For the public health official, there is the awareness that a sustained power outage would quickly create medical emergencies that the system might be inadequate to handle. This kind of occupational stress, this alertness to a threat that does not manifest most of the time, is part of what it means to work in space weather management. It is a different kind of stress than dealing with an acute crisis. It is more like the stress that air traffic controllers experience, this constant awareness that something could go wrong, this constant attention to vigilance, this need to stay sharp even when nothing is currently happening. Most people outside of these fields do not experience this. For the general public, the threat from space weather is even more abstract than it is for the specialists. The storm is happening, but most people are not directly experiencing any negative effects. The aurora is beautiful, the power is still on, life goes on, the threat remains in the realm of knowledge, not experience. This creates a communication challenge for scientists trying to raise awareness. How do you create appropriate level of concern without creating panic? How do you encourage preparation without sounding alarmist? How do you communicate a real risk that is not immediate? One approach that has been used is to frame space weather preparedness not as a unique concern, but as part of broader emergency preparedness. Every household should have an emergency kit with water, food, first aid supplies, and important documents. Every household should know how to get information during an emergency. Every household should have a plan for where to go and how to stay in contact with family members if normal communication systems go down. These are recommendations that apply regardless of the source of the emergency. A solar storm is just one possible cause. Another approach is to focus on the infrastructure level rather than the individual level. The messaging is directed at utilities and satellite companies and government agencies rather than at the general public. The goal is to drive investment in preparedness at the institutional level, where the resources exist to do the most good. This is less about raising individual awareness and more about raising institutional awareness and institutional commitment. A third approach is what we might call the interesting science angle. The sun is fascinating. The aurora is beautiful. The physics of how the solar magnetic field works is intellectually compelling. Teaching people about the science, not primarily for the sake of preparedness, but just because it is interesting, has the side effect of increasing awareness. A person who has learned something about how the sun works and why auroras occur and what a coronal mass ejection is has a foundation of understanding that makes them more receptive to information about solar storm risk when they encounter it. All of these approaches are being used simultaneously by different organizations and individuals. There is no single unified message, but there is a general trend toward greater awareness and engagement. At the international level, there is coordination happening through various forums. The International Space Environment Services, a cooperative network between space weather centers in multiple countries, issues forecasts and shares data. The United Nations is beginning to engage with the space weather community about the global nature of the risk and the need for international coordination in response. UNESCO has designated space weather as an area of concern that should be addressed through international cooperation. But international coordination, while important, is limited by the fact that space weather does not respect borders. The sun does not know what country it is sending a coronal mass ejection toward. A storm that affects one nation affects others. But the infrastructure that is vulnerable, the power grids and communications networks and satellites, operate at national and regional levels. There is no unified global power grid. There is no unified global emergency response system. Each country has to manage its own preparedness. This creates a situation where a single weak link could drag down the resilience of a more interconnected system. If one nation's power system is knocked down and stays down for months, the consequences are not limited to that nation. Global trade is disrupted, supply chains are interrupted, the economic effects ripple outward. In a highly interdependent global economy, a major regional disaster becomes a global event. This is actually one of the more under-discussed risks from extreme space weather. It is not just the local consequences within the region where infrastructure fails. It is the global consequences of that local failure in a world where most countries depend on importing goods and services from elsewhere. This is why some economists and policy experts have started raising the profile of space weather risk beyond the traditional space weather and emergency management communities. They are making the argument that from a business continuity and global economic resilience perspective, space weather preparedness should be a higher priority. The potential global economic impact of a major solar storm is large enough that even a relatively modest expenditure on prevention is justified from a pure cost-benefit standpoint. But arguing on economic grounds, while it appeals to certain audiences, does not necessarily translate into action if the decision-making processes are divided among many different institutions with many different priorities. The utility company wants to minimize costs. The government agency wants to minimize liability. The satellite company wants to maximize reliability while minimizing expenditure. Each institution has its own calculations and its own incentives. It is only when all of these institutions face a common shock, an actual failure that affects them all at once, that they tend to align around a common solution. And that common shock is what everyone is hoping does not happen, but what space weather researchers acknowledge is statistically likely to happen within the next few decades at some level of severity. The current storm, if it holds at the intensity it has reached and does not develop secondary impacts that cause significant damage, will provide a near miss that increases urgency without causing catastrophe. The ideal outcome from a certain perspective. But the world is not always cooperative about providing ideal outcomes. Now I want to shift focus to something that most people never think about, and that is the way that solar cycles and patterns connect to long-term climate on Earth. The relationship is real, though more subtle and complicated than popular understanding often represents. The sun's total energy output, the total amount of radiation it produces across all wavelengths, varies slightly over the 11-year solar cycle. At solar minimum, the output is lower. At solar maximum, the output is higher. The difference is small, only about 0.1% of the sun's total output, but 0.1% of an enormous number is still a significant amount of energy. That variation in the sun's total output can affect Earth's climate. More solar energy in is more warming, less solar energy in is less warming. During the active phase of the solar cycle, when the sun is at maximum, slightly more energy reaches Earth. During the quiet phase, slightly less. If you look at the temperature record over several solar cycles, you can sometimes detect a small signal corresponding to these changes in solar output, a tiny fluctuation riding on top of the longer-term trends. But the effects are actually more complex than just the total energy output. The distribution of that energy across different wavelengths matters. A change in ultraviolet radiation has different effects than a change in infrared radiation. The ultraviolet photons can split molecules in the upper atmosphere and affect chemistry there. The visible and infrared radiation drives heating. These different effects play out at different altitudes and in different ways. Additionally, the solar wind intensity varies with the solar cycle. The solar wind is constantly pushing against Earth's magnetosphere, compressing it on the sunward side and stretching it on the nighttime side. During solar maximum, when the solar wind is more intense, the magnetosphere is compressed more. This affects how the upper atmosphere is heated and can have subtle effects on atmospheric circulation patterns. None of these effects is large enough to overwhelm the current trend of warming caused by greenhouse gas emissions. The changes in solar output over the cycle are much smaller than the energy being added to the atmosphere by the accumulation of CO2. But they are still real, and they are worth understanding. There is also a more controversial mechanism that some researchers have proposed, involving cosmic rays and cloud formation. The idea is that the solar wind, by deflecting cosmic rays away from Earth, affects the number of cosmic rays that reach the atmosphere. Cosmic rays can see cloud formation. More cosmic rays means more clouds. More clouds means more reflection of solar energy back to space, which would cool the planet. Less cosmic rays means fewer clouds and more warming. During solar maximum, the solar wind is stronger and deflects more cosmic rays, which by this logic should mean fewer clouds and more warming. During solar minimum, fewer cosmic rays are deflected, so there are more clouds and cooling. But the evidence for this mechanism is disputed. Some studies support it, others find the effect to be much smaller than proposed or not present at all. It remains an area of active research, and there is not yet a scientific consensus on whether it is a significant factor in climate variation. What is not disputed is that solar activity does have some effect on Earth's climate. The question is how much, and what are the mechanisms, and how does that background variation in solar activity interact with human-caused climate change? One thing that is clear is that we are not currently in a period of unusual solar activity that could explain the warming observed over the last several decades. The Sun, if anything, has been slightly less active over the past 50 years, producing a very slight cooling influence. The warming that we observe is overwhelmingly attributable to greenhouse gas emissions, not to increased solar activity. Some of the early skepticism about global warming was based on the idea that the warming might be caused by increased solar activity, but that hypothesis has become increasingly untenable as the solar data has accumulated and shown no strong upward trend in solar activity over the relevant period. During the current approach to solar maximum, there will be slightly more solar radiation reaching Earth than there was during the recent minimum. This could provide a slight additional warming on the order of a few hundredths of a degree Celsius during this period. It is a real effect, but small compared to the warming being caused by greenhouse gases. The connection between solar activity and climate is interesting scientifically, but it is important not to overstate it or use it as an argument to downplay the human role in current climate change. The Sun's activity has varied in the past and will vary in the future, but the current warming is not driven by solar variations. However, this does connect to something important about forecasting and prediction. When scientists make climate projections looking decades into the future, they have to include assumptions about solar activity. They assume that over the long term, solar cycles will continue with roughly the same characteristics they have had historically. They assume some average level of solar activity. But what if the Sun enters a period of particularly low activity, like the Maunder minimum, a period lasting about 70 years in the 17th century, when solar activity was extremely suppressed and the auroras almost completely disappeared? The occurrence of a Maunder minimum is not predictable at present. We do not understand what triggers the Sun to go into such an extended quiet period. We only know it happened at least once in recorded history and may have happened other times further back. If another Maunder minimum were to begin, the reduction in solar output would provide a small cooling effect that could partially offset some of the warming from greenhouse gases. The global temperature would still increase, but not as much as it would without the Maunder minimum effect. Conversely, if the Sun enters a particularly active phase, if we experience a period of particularly strong solar cycles, the additional solar energy would add to the warming from greenhouse gases. The warming would be stronger than it would be otherwise. Scientists project a range of outcomes for future climate, and the variation in solar activity is one source of uncertainty in that range. It is not the dominant source, but it is one of several factors that contribute to the range of possible futures. What is clear is that whatever solar activity occurs, the greenhouse gas warming is going to be the dominant signal. The solar modulation is small on top of it, but it is still there and worth understanding. The other reason to pay attention to the sun's activity, of course, is the space weather risk that we have been discussing. The solar cycles affect not only the long-term radiation balance, but also the frequency and intensity of eruptive events. Solar maximum is when the big storms are most likely. This is going to be true regardless of whether we are also in a period of unusually high or low average solar output. The sun, during its maximum phase, will produce more events than during the minimum phase, and some of those events could be directed at Earth. So we are entering a period where the probability of a space weather emergency is elevated for the next year or two. We are also entering a period when the solar input to Earth's climate will be slightly higher than it was at the recent minimum. These are independent effects, but they are both real. For the immediate future, the space weather risk is the more urgent concern. In the longer term, if solar cycles continue to behave as they have historically, the climate signal from solar variations will remain small relative to the greenhouse gas signal. But in the near term, keeping the power on and the satellites working is the priority. This brings us to the present moment and what is likely to happen in the coming hours and days. Part 3 of 3, the current storm is expected to continue for another 12 to 24 hours at the time of this recording. The magnetometer data suggests that the main impact of the coronal mass ejection has already occurred, with the peak of the disturbance happening several hours ago. The satellite data suggests that the cloud of plasma is passing over Earth's magnetosphere, with the most intense interaction now in the past. But forecasters are cautious about declaring victory too early. Secondary disturbances can develop. The magnetosphere can respond in ways that are not always perfectly predicted by models. There is still a window of heightened risk for about another day. After that, the probability of significant additional impacts drops substantially. If the pattern holds and no major problems develop, grid operators will begin the process of easing off the heightened alert status they have maintained. Equipment that was taken offline as a precaution can be brought back into service. The tempo of monitoring can decrease. The staffing levels can normalize. The crisis, if it was ever truly a crisis, was successfully managed. The satellites that took shelter in safe mode will gradually return to normal operations as their operators assess whether any damage occurred and begin rebooting systems. In most cases, the spacecraft will emerge from the storm intact and ready to resume their missions. Some may take days to fully recover. A very small percentage might have suffered permanent damage and may operate at reduced capability or not at all. But the expectation, based on the intensity of this storm and the preparations that were made, is that most will be fine. For the astronauts on the International Space Station, they will remain in the radiation shelter until the official all-clear is given by mission control. It is probably not an enjoyable confined space for extended periods, but it is the right call. Once the background radiation levels return to normal, they will be able to resume their normal work and movement through the station. For the general public, the aurora will likely persist for one more night, or possibly two, depending on how the magnetospheric recovery unfolds. After that, the skies will return to normal, at least in terms of visible auroral displays. But the storm will not be forgotten so quickly. The pictures and videos are already being shared widely. The story is now part of the collective memory. For a generation of people who saw the aurora from places where they had never seen it before, it is a story they will tell. The night the sky lit up green. The night the sun showed its face. In the days and weeks to come, the investigation into exactly what happened will continue. Scientists will analyze the data collected by all the various satellites and ground instruments. They will try to understand exactly what magnetic configuration in that particular sunspot region led to the eruption. They will try to refine their understanding of how the ejected plasma traveled through space and interacted with Earth's magnetosphere. They will try to improve their models so that the next time a similar event occurs, the forecast will be even more accurate. The storm will be documented and catalogued. It will be added to the historical record of known space weather events. Future researchers will use the data from this storm to test new theories and models. The event that seemed traumatic when it was unfolding will become a data point in a larger data set, a piece of the puzzle of understanding the sun's behavior. But while this particular storm is passing, the underlying reality remains. The sun has entered the active phase of its cycle. The conditions that produced this storm will recur. The sunspots will continue to evolve. The magnetic tangles will continue to form. The eruptions will continue to happen. The only question is which ones will be directed at Earth and which ones will miss us. We are essentially entering a period of elevated vulnerability that will last for roughly the next year to year and a half. During this time, every time a coronal mass ejection is ejected from the Sun, there is a possibility that it could be directed toward us. The probability is not huge, but it is non-zero, and if one does hit us, and if it is particularly powerful and oriented perfectly to maximize its effect, the consequences could be severe. The preparation for that possibility is what has to happen now during this window. The infrastructure improvements, the hardening of vulnerable systems, the coordination between agencies, the planning for emergency response. These things need to be prioritized and funded and implemented while the threat is salient and people are paying attention. Because the danger with space weather is that the threat is intermittent. Most of the time, most years, nothing catastrophic happens. The power stays on, the satellites work, life goes on as normal, the infrastructure works as designed, and there is no need for the enhanced protection or the emergency protocols. It is easy, under those conditions, for urgency to fade, for the budget to be cut, for the focus to shift to other priorities, for the preparations to become less robust. And then, when the next major storm does hit, after years of reduced vigilance and reduced investment, the consequences can be worse than they need to be. The infrastructure has been allowed to deteriorate, the backups have been cut, the trained personnel have moved on to other jobs, the response is slower and less effective. This has happened before with other types of disasters. The preparations and lessons from one earthquake or hurricane or flood tend to fade over time. The investments in resilience are deferred. The next major event, when it comes, catches people less prepared than they might otherwise be. Then, the cycle repeats. The event causes damage and suffering, lessons are learned, investments are made, resilience is improved, and then, over time, that resilience is allowed to erode again. For space weather, we have the advantage that this current storm is providing a visible reminder of the risk. Researchers, utilities, satellite companies, governments can point to this event and say, "This actually happened." The risk is not theoretical. That is valuable. That is leverage for driving change. But the window of opportunity is limited. If the damage from this storm ends up being minimal, the sense of urgency will begin to fade within weeks or months. Without sustained attention and pressure, the improvements will be slower and less comprehensive than they could be. This is where individuals actually matter. People who learn about space weather and its risks, who understand the vulnerabilities in the infrastructure we depend on, who care enough to push for action. The collective attention of an informed public can drive policy change in ways that technical arguments alone cannot. If you are watching this and you have learned something about space weather that you did not know before, the next step is to actually engage with it. Share what you've learned. Talk to people about it. When you see news coverage of this storm, engage with it thoughtfully. When you see politicians or utility executives or government officials make statements about infrastructure resilience, think critically about whether they are taking space weather seriously enough. Demand that your representatives in government understand this issue. Ask them what plans they have for making sure the power stays on and the critical systems keep working during a solar maximum. Look at the infrastructure in your community and think about what would happen if the power went out for weeks. Think about your own preparedness. What would you do? What supplies would you need? What would your family do? These are not alarmist questions. These are reasonable questions to ask about a known risk. The sun is not going away. The solar cycle is not going away. The 11-year rhythm of solar activity is fundamental to the sun's nature. So the risk periodically is always there. The only question is whether we are taking it seriously enough. Right now, at this moment, the answer is probably not yet. There is more that could be done. There is more investment that could be made. There are more partnerships that could be formed between space weather researchers and infrastructure operators. There are more international agreements that could be put in place. There is more redundancy that could be built into critical systems, more resilience, more backup power, more hardened transformers, more redundant satellites, more diversified communications pathways. All of this is possible. It is not impossible. It is just a question of will and resources and priority. And every time a major solar storm occurs, the will to do these things increases, at least temporarily. The resources become a little bit easier to justify. The priority creeps higher. Over time, through a series of storms and near misses, the infrastructure gets better, the resilience improves, the risk decreases, but it is a slow process, and it is not one that moves in a straight line. There are setbacks, there are budget cuts, there are people who do not believe the risk is real or who think other priorities are more important. There are institutional barriers and bureaucratic challenges. Making a complex technological society more resilient to a specific risk is harder than it sounds, and yet it is necessary. Because the storm that is happening right now is not a one-time aberration. It is a normal part of how the universe works. The sun erupts, the particles travel through space, they hit the Earth. It happens. It has happened countless times before we are here. It will happen countless times after. We are just the first civilization that has built infrastructure vulnerable to it. So we have to adapt. We have to harden what we can harden. We have to back up what can be backed up. We have to prepare for the interruptions and the disruptions that are statistically certain to occur at some point. The people who are already working on this, the space weather researchers and forecasters, and the engineers and emergency managers who take this seriously, they have chosen a difficult path. They have to maintain vigilance for a threat that mostly stays quiet. They have to advocate for resources to prevent a disaster that has not happened yet. They have to prepare for scenarios that they hope will never occur. It is not easy. It is often thankless work, but it is important work. And they are not asking for much. They are not asking for the entire global economy to be restructured around space weather risk. They are asking for the power grid to be a little bit more robust. They are asking for redundant communications. They are asking for better satellites and better monitoring. They are asking for plans and protocols. They are asking for resources. What they are asking for is that when the sun produces a violent eruption, the consequences do not cascade into a civilization-wide catastrophe. That seems like a reasonable ask. That seems like something that should be a priority. Here is the thing that I think is easy to miss when you are focused on the technical aspects and the infrastructure challenges and the policy questions. There is something profound about the fact that we now know this threat exists. For most of human history, the sun was just the sun. It was a source of light and warmth. It was painted and worshipped and written about. But its behavior, its capacity to produce eruptions that could affect the Earth, that was not known. That was not part of the human understanding of the world. We figured it out. We built instruments that could see the sun in detail. We sent satellites out into space to observe it. We collected data over decades. We understood the physics. We made the connection between eruptions on the sun's surface and disturbances in the Earth's magnetosphere. We figured out that this was not a spiritual thing or a mystical force. It was physics. It was a knowable, predictable, manageable phenomenon, and having figured that out, we now have a choice. We can use that knowledge to protect ourselves, or we can ignore the knowledge and hope that nothing bad happens. Most of human civilization has historically chosen the latter, because the cost and the complexity of protection was too high. But we are increasingly in a position where we can do better, where the cost of protection is bearable, where the knowledge can actually be transformed into resilience. Whether we actually do that is an open question. It depends on all of us. It depends on whether the people who understand the risk take the time to communicate it clearly. It depends on whether the people who hear that communication take it seriously. It depends on whether that concern can be translated into political will and policy change and infrastructure investment. It depends on whether the next time you're looking at a news story about the power grid or about satellites or about space weather, you actually read more than just the headline. You learn something. You understand a little bit more about how the world works. You develop an informed perspective on a risk that is real but not well known. It depends on whether you talk to other people about it, whether you share what you have learned, whether you contribute your voice to the conversation about how important this is. It depends on all of that, and that is actually kind of remarkable. A phenomenon that originated 93 million miles away, inside a star, that travelled through the vacuum of space for a day and a half, that hit the Earth's magnetosphere and caused auroras to appear in the sky, that could have caused widespread disruption to the electrical infrastructure that modern life depends on, is now something that you understand. It is no longer invisible. It is no longer mysterious. It is something you can think about, talk about, and potentially influence through your own choices and your own voice. The sun will continue to be the sun. It will continue to cycle through its active phases and quiet phases. It will continue to produce eruptions and coronal mass ejections. It will continue to rain charged particles down on the Earth. These are not things we can control. These are not things that will change because we want them to. But what we do in response to that reality is something we can control. We can ignore it. We can hope for the best. We can let it remain someone else's responsibility. Or we can engage with it. We can demand better. We can insist that the infrastructure we depend on be resilient. We can make sure that the people whose job it is to watch the sky and warn us about what is coming actually have the resources to do that job well. The storm that is happening right now, that is painting the skies green and pushing waves of charged particles through the magnetosphere, is a reminder that we live in a dynamic universe. The universe does not work according to the rules of human convenience. The sun does not care about our schedules or our expectations. It erupts when the magnetic field lines twist up and reconnect. It sends plasma through space. It affects the planet. It creates beauty and it creates danger. Looking up, if you can, at the aurora that this storm has produced, is a way of seeing that directly. It is a way of connecting, visually, to something that is happening at the intersection of the sun and the earth, at the boundary of the magnetosphere, in the thin layer of atmosphere where atoms and molecules are being struck by particles and emitting light. It is beautiful. It is science. It is the universe revealing itself to anyone who takes the time to look. And it is also a wake-up call, a reminder that the infrastructure of civilization is more fragile than we usually imagine, that the power we take for granted is dependent on systems that can fail, that the protection we have is not automatic or guaranteed, that the future is not something that happens to us, but something that we help create through the choices we make and the investments we prioritize right now. The next few years will be telling. As we move through solar maximum, as the probability of major events remains elevated, as the sun continues its cycle, we will see whether the lessons of this storm translate into action. We will see whether preparedness improves. We will see whether the vulnerable systems get hardened. We will see whether the institutional barriers to change can be overcome, and if the next major storm that hits us hits a society that is better prepared than before, then this current storm will have been worth the attention and the concern. The beauty of the aurora will have been matched by something more abstract but equally important, the satisfaction of knowing that we have used the warning to build resilience. That is the real story here, not just the storm itself, not just the eruption on the sun, not just the physical phenomena that are spectacular and worth understanding. It is what we do with that understanding, how we respond, how we prepare, how we use our knowledge to protect what matters. The sun has given us that knowledge. It has shown us what it can do. The question now is what we will do with what we have seen. Look up, if you can. See the aurora if it is visible where you are. Take a picture. Share it. And then think about what you have learned from this event. Carry that knowledge forward. Apply it to how you think about the world. Use it in whatever way you can to push for the changes that need to happen. The universe is not going to change. The sun will not stop cycling through its active phases. The solar wind will continue to blow. The magnetic field will continue to twist and reconnect and produce eruptions. That is what stars do. That is what this universe is. But we can change. We can respond. We can prepare. We can build something better than what we have now. We can create a civilization that is resilient to the forces that the universe throws at us, not invulnerable. The universe is too powerful for that, but tough enough to endure, smart enough to survive, thoughtful enough to take seriously the risks we can see and predict and plan for. That is the work that matters now, and it is work that is ongoing. It is work that requires attention and resources and commitment. It is work that is difficult and often frustrating, because the payoff is not visible if it is successful. If the infrastructure is hardened and the grid is protected, and the next major storm comes and nothing bad happens, then all of that work will have been invisible. It will have prevented a disaster that never occurred. That is what successful disaster prevention looks like, and it is often underappreciated precisely because the disaster never happened. But think about it from the other direction. Imagine a future where a major solar storm hits a vulnerable infrastructure and causes months of power outages and all the cascading consequences that flow from that. Now imagine going back in time and being able to spend a fraction of the cost of recovery on hardening the infrastructure to prevent it. The choice seems obvious. We are right now in that moment of choice. We're in the window when the previous disaster did not quite happen, when this current storm provided a near miss that created urgency but not catastrophe. This is when change can happen. This is when we can make the investments that will matter. Whether we actually do that is up to all of us. The scientists have done their part. They have explained the risk. They have provided the data. They have offered the solutions. The infrastructure operators have the technical capability to implement those solutions. The government agencies have the authority to mandate them. What is missing is the sustained focus, the political will, the collective agreement that this matters enough to warrant action. That sustained focus, that political will, that collective agreement, those things come from people understanding the issue and caring about it and pushing for change. Those things come from you, from your attention, from your voice, from your choices. So think about it, learn about it, talk about it, demand better from your leaders and your institutions. The next storm might not come for months or years, but it will come. And when it does, you want to live in a world that was prepared for it. That is the real story here. Not the beautiful aurora, not the immediate drama of the power grid operators watching their screens, not the astronauts in their shelter on the space station. Those are just the opening act. The real story is what happens next, how we respond, what we build, what we decide to prioritize. The storm is happening now, but the future is still ours to shape. Continuation. The final hour. Because here is what happens after the storm passes and the headlines fade. The satellites come back online, the grid stabilizes, the aurora disappears, the social media feeds move on to the next trending story. And life goes back to something that looks normal. But underneath that normality, there is something that has shifted, at least in certain circles. There are conversations happening in boardrooms and government offices and research laboratories that are different from the conversations that were happening a month ago. Some of these conversations are about immediate improvements. Utilities are looking at their transformer inventory, asking themselves whether they have enough spares in the right locations. Satellite operators are reviewing their telemetry data from the storm, learning what worked and what did not. Emergency managers are updating their playbooks, incorporating what they learned from the actual response to an actual event rather than just simulations. These are practical, concrete improvements that will happen or not happen based on budgets and priorities in the next few months. But there are also longer-term conversations happening. Conversations about what a truly resilient infrastructure for the next solar maximum would actually look like. What would it cost? What would it take to implement? Who would be responsible for different pieces? How would you even coordinate something that complex across so many different organizations and jurisdictions and countries? These are harder conversations. They do not have simple answers. They involve trade-offs and compromises and difficult choices about resource allocation. They involve people with different incentives trying to find common ground. But they are happening. They are real, and they would not be happening, or at least not with the same urgency, if the storm had not occurred. This is the reality of disaster prevention in a democratic society. The ideally optimal time to invest in prevention is before anyone has experienced the disaster. But the political and economic reality is that it is much easier to get resources allocated after a close call. A storm that threatens but does not quite destroy provides that ideal window. It is enough to prove the risk is real. It is not enough to cause so much damage that the recovery itself is paralyzingly expensive. But windows like this close. Within a year, maybe two, the sense of urgency will fade again if the next major storm does not occur. The budgets will get tight. Other priorities will compete for attention. The infrastructure improvements that seemed urgent in the immediate aftermath will become less so. Some will be implemented, many will not, and the gap between the actual infrastructure and the ideal infrastructure will remain. This is the reason that some space weather researchers have started thinking about this problem differently. Instead of trying to prevent a catastrophic outcome by pushing for massive infrastructure hardening, they are thinking about resilience in a more distributed way. What if the focus was not on preventing all possible solar storms from causing any damage, but on making sure that a major outage, if it happened, could be managed and recovered from in weeks rather than months or years? This is actually a more realistic goal. You probably cannot harden the entire electrical grid against a Carrington-level event. It is too extensive. It is too interdependent. It is too economically challenging. But you might be able to make it so that even if major portions of the grid go down during such an event, the recovery time is much shorter. You might be able to make sure that essential services like hospitals and water treatment facilities have the backup power and redundancy they need to keep operating. You might be able to make sure that critical control centers have the communication capability they need to coordinate response, even if the broader internet is down. This approach is actually gaining some traction among emergency managers because it is more pragmatic. It acknowledges the limitations of what can be hardened and focuses on what can actually be achieved with realistic budgets and realistic constraints. It is not the ideal solution, but it might be the best solution that is actually achievable. There is another dimension to this that does not get discussed very much, and that is the international cooperation angle. Because the power grid in one country does not exist in isolation. The modern global economy is deeply interconnected. If the power goes down in Europe for an extended period, the consequences ripple across the entire world. Supply chains are disrupted, financial markets are disrupted, communications are disrupted. A truly severe geomagnetic storm could plausibly affect multiple continents simultaneously. It is not a regional disaster. It is a global event. And yet the response to it would necessarily be coordinated at a national level by different governments with different priorities and different capabilities. Some countries have much more advanced emergency management systems than others. Some have more redundancy built into their infrastructure. Some have better communication between space weather forecasters and infrastructure operators. If a major global-scale storm occurred, the response would be as uneven as the preparedness. Some regions would recover quickly, others would struggle for months. The human consequences would vary wildly depending on where you were and what kind of infrastructure your region had in place. This is a genuinely difficult problem to solve because it requires countries that are geopolitical competitors to cooperate in the space weather domain. It requires sharing information about vulnerabilities and capabilities. It requires coordination on response protocols. It requires trusting that other countries are taking the threat seriously and investing in preparedness. Some progress has been made. The United Nations Office for Outer Space Affairs has established a working group on space weather. Various countries have representatives who meet and discuss coordination. International bodies like the International Telecommunications Union have started thinking about space weather resilience for communications infrastructure. But it is slow progress. The political barriers to truly effective international coordination are substantial, and yet the physics does not care about political boundaries. The sun does not negotiate. A coronal mass ejection travels in straight lines determined by the magnetic field configuration at the time of its launch. Where it goes, where it hits, what it damages, these are determined by physics and orbital mechanics, not by human politics. This is one of the reasons that some futurists have started thinking about space weather as a driver of potential human conflict rather than cooperation. The thinking goes like this. If a major solar storm causes severe damage in one country but not in others, there could be geopolitical consequences. There could be accusations that others did not share information that might have helped. There could be disputes over resource allocation for recovery. There could be pressure from damaged regions on their governments to retaliate or take aggressive action against countries perceived as having failed to cooperate. This is speculative, but it is not frivolous. Disaster situations do create political stresses. They create winners and losers. They create opportunities for blame and recrimination. And geomagnetic storms, if severe enough, would hit different places differently based partly on geography and partly on random chance about where the cloud of plasma happens to be directed. Managing the political consequences of a large-scale space weather disaster would be just as challenging as managing the technical consequences, and the two would interact with each other. Political instability makes technical recovery harder. Technical disaster makes political stability harder. They feed into each other. None of this is inevitable. Good planning and good communication and good faith cooperation could prevent most of these problems. But it requires taking the threat seriously enough to do the planning before the crisis hits. And we are not quite there yet as a global civilization. What we have instead is a patchwork. Some countries taking space weather seriously. Some utilities and satellite companies being proactive. Some government agencies maintaining good forecasting capabilities and good communication with the private sector. But also a lot of places where the preparedness is less robust, where the investment is less substantial, where the planning is less detailed. The uneven preparedness is actually a form of risk, not risk to the space weather forecast, but risk to the global system. If a major storm hits and some regions are severely affected while others have minimal impact, the social and political stresses could create problems that compound the technical problems. This is the larger systemic risk that does not get discussed very much in public conversation about solar storms. The immediate risk is the one that gets talked about, the risk to the grid and the satellites and the infrastructure in your region. But the larger risk is the global system risk, the possibility that a space weather event becomes not just a technical disaster, but a political and social one as well. Managing that risk requires a level of global coordination and cooperation that has proven difficult to achieve on other pressing issues: nuclear non-proliferation, climate change, pandemic response. All of these require international cooperation on understanding risks and coordinating response. And in all of these cases, the level of cooperation achieved has been less than what experts say is optimal. Space weather is perhaps slightly easier than some of these because it is less directly tied to national interests. No country benefits from a solar storm. There is no state that wants it to happen. The incentives for cooperation are more aligned than they are on, say, climate change, where different countries have different interests related to emissions and economic development. But the incentives are still not as strong as they could be. If the cost of preparedness is high and the probability of a damaging event in any given year is low, then from an individual nation's perspective, the incentive is to let other nations do the heavy lifting. It is a classic collective action problem. Everyone would be better off if everyone invested in preparedness. But any individual country can benefit by not investing and hoping that the disaster does not hit them. This is why the window created by this current storm is so important. While attention is focused, while media is covering the topic, while researchers are speaking up, while there is a sense that the risk is real and immediate, that is when change can happen. That is when countries and utilities and operators can be pushed to do more than they would do if it was just another abstract risk being discussed at conferences. But that window is closing. Even as this storm is still ongoing, even as the impacts are still being measured, the public attention is already beginning to shift. The news cycle moves on. The next story emerges. The aurora fades. Life returns to normal on the surface. The question for the next few years is whether the deeper changes persist, whether the conversation that started during the storm continues, whether the improvements that were planned get funded and implemented, whether the sense of urgency translates into actual action. Based on historical patterns with other types of disasters, the answer is probably mixed. Some things will improve, some budgets will be allocated, some people will take the threat more seriously, but the level of improvement will probably be less than what was discussed during the height of the crisis. And if 5 years go by without another major solar storm hitting, the urgency will fade to the point where new infrastructure investments become harder to justify. This is the tragedy of the long-term risk. The optimal strategy is consistent vigilance and continuous improvement, but that requires maintaining political and social will for something that is not immediately threatening. Most human societies are better at responding to acute crises than at preventing chronic risks. We are better at fighting fires than preventing them. Space weather is ultimately a chronic risk that is occasionally acute. Most of the time it is just background information, something that specialists think about but most of the world ignores. Then, periodically, it becomes acute. A major event occurs, attention spikes, resources flow, and then it fades again. The challenge is to use those acute moments to make changes that persist through the chronic periods, to build momentum toward an infrastructure that is resilient not because of fear in the moment, but because of understanding that has accumulated over time. This current storm is a moment like that. It is a moment where the acute crisis is driving attention to the chronic risk. What happens in the next months and years will partly determine whether that attention translates into real, lasting change. Now there is one more dimension to this whole story that I want to explore, and it is something that gets far less attention than the power grid or the satellites. And that is the human dimension of living with uncertainty in a technologically complex world. The reason I bring this up is that one of the consequences of understanding space weather risk is that you become aware of something that most people go through their lives not thinking about, which is that the technological systems that we depend on are more fragile than they appear. They work most of the time, they work reliably, but they are built on assumptions that are not always justified. They are connected in ways that create vulnerabilities. They are subject to disruptions that we cannot control. This awareness, this knowledge that the power could go out and stay out for weeks, that communications could fail, that the systems that keep modern life functioning are not guaranteed to keep functioning, this is actually a kind of psychological burden. It is not a burden that everyone carries equally. Some people choose not to think about it. Some people dismiss the risk as unlikely enough not to worry about. But some people who work in these fields, who understand the systems deeply, who know what could go wrong, they carry this knowledge. They live with this awareness. It is a little like knowing too much about structural engineering and then not being able to feel completely safe in tall buildings, or understanding microbiology and becoming hyper-aware of the bacteria and viruses everywhere, or knowing about climate change and thinking about it in the background of every weather event. Once you understand a risk, you cannot fully unknow it. The awareness becomes part of your mental landscape. For space weather researchers and forecasters and grid operators, this awareness is professional. It is part of their job to think about these risks. But it is also psychological. They carry a kind of low-level worry, a background tension that most people do not experience. What is interesting is that this psychological burden actually correlates with something positive, which is motivation to prevent the disaster. The people who are most worried about space weather risk are the people who are most motivated to do something about it. The two are connected. The worry is uncomfortable, but it is productive. It drives action. There is something worth thinking about in that dynamic. The people who care enough to maintain vigilance about a threat are the same people who are burdened by the awareness of that threat. Perfect knowledge would be paralyzing. Ignorance is dangerous. There is some sweet spot of awareness and understanding that allows for productive action without being overwhelming. Finding that balance is part of what experts in these fields do. They carry awareness of the risk without being paralyzed by it. They maintain motivation without being driven by panic. This is actually one of the reasons that public engagement with this topic is important. Because if only the specialists know about the risk, then only the specialists are carrying that psychological burden. They are carrying it within institutions that are designed to handle it. But if the general public became more aware of the risk, more people would be carrying some version of that burden. And the distributed awareness would have power. It would translate into political pressure for action in a way that the specialist awareness alone does not. But there is a balance to maintain. You want enough awareness to drive action. You do not want so much awareness that it becomes paralyzing or generates panic that leads to counterproductive responses. This is actually one of the reasons that space weather communication is tricky. Communicators have to walk a line between informing people about a real risk and not creating irrational fear. They have to convey that the threat is serious and worth taking seriously, but not make it seem like civilization is about to collapse. They have to encourage preparedness without encouraging paranoia. Most of the space weather communication I have seen does this reasonably well. Scientists and forecasters do try to be clear-eyed about the risks without being alarmist. They present the facts and the uncertainties. They describe what could happen in the worst case while acknowledging that worst-case scenarios are not guaranteed. They encourage preparation while avoiding apocalyptic language. But there are always people at the extremes. Some who dismiss the risk entirely as doomsaying. Some who become convinced that civilization-ending disaster is imminent. Most people end up somewhere in between, understanding that the risk is real but not letting it paralyze their lives. And that is probably the healthiest place to be. What this particular storm does, ultimately, is prove that the space weather forecasters and researchers are not making things up. They are describing something real. The aurora was real. The impact on the magnetosphere was real. The concerns of the grid operators were real. The warning systems worked. The forecasts were accurate enough to be useful. The event occurred in a way that was broadly consistent with what experts have been saying could happen. That validation, that proof that the experts know what they are talking about is important. It increases the credibility of future forecasts and future warnings. It increases the likelihood that when the next major storm is forecast, people will pay attention and take it seriously. That is valuable. That is a real improvement in preparedness that comes just from this storm happening and being observed accurately. Now, as we move toward wrapping up, I want to go back to something that is fundamental to all of this, which is that we are living in a unique moment in human history. For the first time, we have the knowledge, the technology, and the capability to understand space weather and prepare for it. But we are also living in a moment where the infrastructure that would be most vulnerable to space weather is only becoming more extensive and more interconnected. This creates a window of opportunity. A moment where the problem is recognized and the solutions are at least partially available, but before the catastrophic consequences of inaction have to be experienced. This window might last years, It might last decades. It definitely will not last forever. At some point, if the problem is not solved, a sufficiently severe storm will occur and the consequences will become impossible to ignore. But we are not there yet. We are still in the window where prevention is possible. The people working to close that window, to implement the solutions, to harden the infrastructure, to coordinate the response, they are doing it largely out of conviction. They believe that the risk is real and worth addressing. They are not doing it because a recent catastrophe forced them to. They are not doing it because the political pressure is overwhelming. They are doing it because they understand the physics and the systems, and they can see what needs to be done. That kind of work, driven by conviction rather than crisis, is worth respecting. It is the kind of work that prevents disasters. It is not flashy. It does not generate headlines. But it matters. At the same time, there is no point pretending that the level of work and investment is anywhere close to what would be optimal. There are gaps. There are vulnerabilities. There are systems that are more prepared than others. There is room for much more to be done. The current moment, with the storm having just occurred and attention focused, is a moment when that gap could be narrowed, when resources could be allocated toward closing it, when the infrastructure could be made more resilient. Whether that actually happens depends on whether the awareness created by this storm translates into action. It depends on whether the conversations happening in the weeks after the storm lead to actual budgets and actual projects. It depends on whether the sense of urgency persists long enough to see improvements implemented. It depends on all the things that depend on collective will and priority allocation and sustained attention. And it depends in some sense on people like you, people who have taken the time to understand the issue, to think about what it means, to recognize that it is important. The researchers and the forecasters and the grid operators and the government officials, they can do their jobs. But they do that job against a backdrop of public attention and political priority. If the public cares, politicians care. If politicians care, budgets get allocated. If budgets get allocated, infrastructure gets improved. The other possibility is that 5 years go by, no major storm hits, attention fades, budgets get cut, the focus shifts to something else. And when the next major storm does eventually hit, the infrastructure is only marginally more resilient than it is now, and the consequences are worse than they needed to be. That is the future we want to avoid. That is what the preparation is for. That is what the conversation is about. The beautiful thing about this moment is that we are not choosing blindly. We are not making a bet on an invisible threat. The sun just showed us what it can do. The aurora is the proof. The disruptions, small as they were, are the proof. The grid operator's vigilance is the proof. The astronauts in their shelter is the proof. We have seen the threat. We know it is real. We have the capability to respond. The question is whether we have the will. So what happens now is up to us, not just the engineers and the forecasters and the officials, but all of us collectively. The attention we pay, the conversations we have, the pressure we put on our institutions to take this seriously, the resources we are willing to allocate to prevention, the trade-offs we are willing to make. Because here is the final truth about space weather and solar storms, and the vulnerability of modern civilization to forces we cannot control. We cannot stop the sun from erupting. We cannot stop the particles from traveling. We cannot stop the magnetosphere from being pushed and compressed and affected. But we can build systems that are resilient to what the sun throws at us. We can create infrastructure that continues to function even when disrupted. We can prepare in ways that reduce the damage and shorten the recovery. We can do that. We have the knowledge. We have the technology. We have the resources. The only question is whether we choose to. The storm that happened today is not the only reminder we will get. There will be others. The sun will keep cycling. Sunspots will keep forming. Eruptions will keep happening. Some will miss us. Some will hit us. The next one that hits could be in weeks or years or decades. We do not know, but it is coming. The question is whether we will be ready. That is the real story, not the storm itself, but what we do in response to it. Whether this moment of awareness and attention translates into action and resilience. Whether we use the warning to improve our defenses. Whether we prove that we can take a threat seriously and respond to it even before it becomes catastrophic. That is what will matter in the long run. That is what will determine whether this storm becomes a turning point or just another dramatic weather event that fades from memory. The choice is ours. The moment is now. And the sun is still watching, still burning, still cycling through its phases, still occasionally erupting with forces that we cannot control, but increasingly can understand and prepare for. That is where we are. That is what we are facing, and that is what comes next.